Okay, so welcome to demonstration video 3. We're looking at ggplot with large data set for this course B08 Data Visualization. So let's go to Org Studio. So what we're going to do here is import three packages that we need called grid, ggpub and ggRepel. So the purpose of grid is to multiple plots together. ggpub will let us create these plots, the different plots we're going to create, and ggRepel also will make sure that when we put labels on plots that they don't overlap each other. So we're going to import our Irish boy names again, and as per previously, get rid of the first column by putting it into the row names, so we don't have that there. And we can do the same with the Irish girl names. So we're getting with that numerical data as for each of the cells, and just column names and our row names contain the labels that we have. Like before, we're going to look at 1964 versus 65. If we look at that for the boys' names, we see that the correlation is very, very high. They're at 0.99. If we do that same for the girl names, again, you see that that correlation is actually quite high. You can check the years there by looking at 1964 and 65 and also plot them like that to see with base R that the plot is good. We can do the same with ggplot. Just have to note that we're reading in the data for X as a data, and then we're setting the X-axis to be X1 1964 and the Y-axis to be X2 1965. If you do that on its own, we'll just get the background in essence. And if we add additional things, we can put points like blue points for these years as well. So you can see there we have our blue points added there. We can toggle these and change their size to make them smaller, change the shape as well, make them more transparent, and turn off the legend if that appears. So if we do that, you can see you've got smaller points and a better sense of the data. We can also take a log of this data. So if we do this part only and take the log only, you can see you get a better sense of the distribution of names that are present. And what we can do is scale the X and Y axis to be continuous, going from 1 to 8, which they are more or less already, and add add set the names to be the column names of the years. So let's run all this function. So you can see there we have labeled 1964 and 1965. And it's quite easy then to change that for the girls. We just put XG instead of X. And if we do that, then we get a similar plot. So you can see that this plot setup is quite generic. What we can do next is add a smoother. So we're looking at the line of best fit between the 2 years. We're just adding that function smooth with a red line there, showing the line of best fit. If we can change the size of this line, if we want to make it bigger or smaller, and then transparency as well. So we can change that and make that much more transparent if we so choose. So all of these features are things we can toggle depending on what we want. What we can do as well is add on further annotation on this smoother line. So what we're putting in here is we're pasting in the R value. So we're saying paste R for the correlation between the years 1964 and 1965, getting the correlation value $2 estimate, and we're rounding that to 3 digits. So we see that that's what we're trying to print. And we see, look at the correlation test for those 2 years. Dollar estimate is the correlation coefficient. So dollar estimate there for correlation coefficients, that's where we got that from. And then we're taking this text and using a series of functions to plot this. So we're specifying the coordinates, so using HJust and VJust, and we're setting the colors, the text color to be black. The font size is 14 here, so it's big enough for this plot. We're using the text grab and grab tree functions and the custom annotation function as well. So there's quite a few functions there all built together, and that will mean that we have to figure out where our grab tree function came from. So that's from grid. So that should work. Let's just check that this works. So there we see the R value would be printed there if it was scaled in the right position. So we can change, we're trying to change the horizontal plotting point to be a little bit bigger. for this narrow plot. So we change H just so we can see there our plot is gone magically. So what we can do is change that down to 1, and hopefully that will reappear. It takes a bit of effort to get it plotted in the right position. And that will change if you're doing plotting out to PDF, but you see it there plotting now. So we can see the correlation coefficient. So it's nice to automate plots like that. We can add on other things. So we can change this to be 1.3. And this is GM text to plot the names, the labels of the names adjacent to their point wherever there is space. So we don't want them to overlap too much, and their size, will change the size to be smaller to fit more. If we see them plotted here, they're very small. So let's make them a bit bigger so we can see them all, or see some of them. So you can see there, James is the most common at the far end. You have Killian and Ulton and Frank. And you can look at the relative frequency of ones over time. So if we look at the difference, say, for a different year, so change this to be column 32 as our comparison. So we need to change that for all the values here. And we just repeat the same thing. We might find a difference there. So now we see that the correlation is much lower. What we see there is that James and Thomas are still common in both years. Finian and Marco are less common in both years. But what you can see is that the relative frequency of genes that are more common, genes names that are more common in 1996 are like Gavin and Ross and Luke and Shane and Sean, relative to their frequencies in 1964, where Gabriel and Ronald and Cornelius were more common back then. If we change this for another year, 1940, number 42, this might be 2012. Again, you can see there's still some names that are common. You see there the likes of Enda, Dermot, Nigel, Kenneth are more rare in 2014. They're more common in 1964. And equally, Oisin, Luke, Alexander, Matthew, Liam, Owen are all more common in 2014. So what you can do is with the girl names, try the same plot. And that's just really, we just need to change these certain values here. And you see it's log scaled here for ease of viewing. Because if we didn't have it log scaled, this would not be as easily visually interpreted. So you can see that that's not, that the limits have to be changed as well. So you can remove them. Yeah, we get a very partial picture of what's going on. So let's look at then an instance where we're sending the same plot, but we're sending it to write it out to a file as a new variable. So we're calling that P1. So if we run this code, it's stored in P1. Nothing happens, nothing is plotted. If we type in P1 and run that, we'll see that this is plotted. What we can do is toggle this factor just to fit the correlation coefficient onto our plot. And then we can run P1 in the console here to see our plot. And what we're going to do is wrap around marginal distributions on top of these. So if we look at GG marginal, you'll see that there's quite a few options here in GG marginal. Where here we're using a densigram type of plot, but there's other ones like a histogram and more options there as well. So if we a box plot, violin, and densigram, we can toggle the margins there if we need more or less space. We can change the color, the bidding approach, and the size as well. So if we try this for P2, we're essentially wrapping these plots together. So we need to scroll too far to P1. We're looking at this part, P1. So we're wrapping this together. So we can see that plot now produced there. What we can do is we can change that to violin. And that's recorded for Fig1. You can see our violin plots. That's not effective for our instance here. Histogram might also be effective. So you can see it's kind of the same approach that we had originally, and other ones that were possible were density plots and as well. So densitograms are a hybrid of a histogram and a density plot. So we can see the density plot here. So you see there that visually the histogram or densitygram are the most effective, it seems. So to plot this out for Fig 1, we can use ggrange to determine the number of columns and rows that we want. Here that's set to 1, hence we got one plot. We can write this to file as well. And we just use ggrange to plot out that figure, and that's saved to file now. So you can create your own plot question for this question using your data from above, and just toggle the number of breaks that you want. So we can change that for 2016 here. We're setting a variable new. So new is that value here. We set it to be P2. So if we look at P2, let's look at that further for P2. So what we can do is make sure we declare new properly. And let's create P2 here and look at that plot. So you can see here we have the plot without the marginal distributions. We can add that onto Fig 2 now and plot that out. So we can see the marginal distributions. We can see that the underlying data is actually comparable for each of these distributions, but the correlation is different. So the frequency of the names in these different years is quite different. What we can do further on this is toggle this code. So now we're going to add labels of colors to show the names using geom text. So you can see here down here at the end, we have quite a complex plot, and we're using the labels as the row names. We're using the color as a factor for that year, and we're checking that there's no overlap and no legend. So if we do this, we'll command, you can see here we have plotted the names on top of our plot. If we can slide this over to see things more clearly. Obviously, we can change the position of the correlation coefficient to somewhere that's nicer. But we can certainly see that we can see the names graphically more easily in this plot. So that's one way we can add labels onto a plot using ggplot. And then what we can also do is plot figures together using ggrange. And we can say the number of columns and rows that we want. Here we're going to do these plots as top and bottom, if they'll appear, so that we can directly compare and contrast them more easily. Obviously, the plotting parameters are something we have to modify depending on what kind of final plot we want. So this kind of indicates how we can build up layers to show our plots more effectively. So you can try these things on your own data sets as well. One thing we can further do with this kind of large data set is measure the extent to which different years are not correlated with each other. So if we look at the correlate test function here, we look at the correlation estimate we looked at before for two particular years of interest. So that could be 1965 versus 1964, for example. They're very correlated, but we know 1964 versus 2016 is not very correlated. Here, we're going to look at the least correlated years. So we're saying if the estimates that our values have less than 0.3, where the one value is less than the other value, so don't double count, we want to print that out. So if we set I want to be one value and I2 to be another value, we can then paste out this information. So we'll get something like this, the different columns and the correlation coefficients. So let's try this loop. So we're looping through each year and then each other year for the comparison. That's why we have this term here to avoid double counting. So if we do this, we'll find that there's one instance where we have number 15. So we can check this here by seeing what they are. 44 we know is 2016. So $15 is going to be, we have to get the call names for X. 1978. That's the least correlated out of this data set. And what we can do is plot that again using the names. So that must mean the Pope John Paul visit effect, I'm suspecting. that affected originating frequencies for a few years. So you can sort of see there different patterns that Jack is much more common in 2016, Harry, Alex, Ryan, Ben, Oisin, whereas Trevor, Enda, Fergus, Wayne, Niall, Keith, Damien were all more common in 1978. So that kind of indicates the names that were more Michael, Davis, Thomas were all more common in 2016 than they were in 1978, but they were common in both. Whereas Carlos, Aaron, Dwayne were kind of rare in both as well. So there's no meaningful differences there. Um, so that that's something we can look at further. So what we can do is that we have a large data set, and what we've done with so far is look at this as if it's a standard wide tabular data, but we can convert our data into tidy data with tidyverse. So to do that, we use the gather function. We're gathering x1, and we're looking at a new key called the year, so that's of interest, and the value. That's the value is the frequency for that particular year. And we're taking the column names for x1. We're reading a new data set because um, you'll find that there may be issues if you have removed the X from the years. So we're leaving that in there. So if we look at the column names, we're looking at each of the years from 1964 to 2016 with the X left in there. I'm using this gather function, which converts the wide data into long data. So just a single command here with X1 as the input. We're getting year and value, and then we have the column names that are basically ordered one after the other. So we have 1964 for the first bundle of names, then 1965, then 1966, and so on. So let's view that to show you what I mean, that we've Jack 1964 NA, Sean 1964 171, and so on and so on and so on. If we look at all the values for Sean there, let's sort them by name. You see it's ordered by year. So all those values are in there for the different years. It's just a long data set. So it's every kind of 2,200 name is shown in our data set. And then there's variations like Sean, Michael, and other things as well. So that's how this is organized. And what we can do now is remove that X. What we're going to do here is, because this is a large data set, we're just going to look at values that have a frequency greater than 200. Well, it's going to remove the NAs from this data set. So if we do that, we can just see that we have the more frequent names here. So we've got Daniel from 1964 was kind of common. James is more common. Michael is even more common again. We have no names with a value of exactly 200 or below that. So what we do is plot these new names in the same way that we did before. So if we do that without this command facet wrap, we can just see the points, but it won't show properly because it'll be trying to plot all the names together. So you can see that over years. You probably can determine that there are certain names that are of interest here, but it's hard to follow. So what you do instead is use the facet wrap function to plot them out for each individual name. So that does every name inside there, and we're presenting name as an argument to facet wrap. So that means it'll iterate the same plot for each individual name. So you can see that it's not very clear here because there's a lot of names here. We're dealing with a large data set. So what we're going to do is write this to a really big PDF with a width and height of 88. So it's a large file size. And we're writing the same thing out. But it'll be easier to see with this PDF. So if we look at a facet wrap as created for this very large data set, we can see that there's lots and lots of names listed here, but they're not very clear yet till we zoom in. So if we zoom right in there, we can see for Dante, Daniel, and Dara, the frequency of the name, and the y-axis indicates the frequency. So you can see that certain names we call more common, like Craig, and other ones like Colm there, and there's lots of examples there of different names with different frequencies over years, but you note that most of them are quite rare. And some kind of ebb and flow like Gareth there or Graham. And if you look at an easy example here, such as John, you can see the trend over time that it decreases in frequency over time. So we go over here to the left-hand point, we have the axes written here, and then the same on the down below. We have each of the years iterated out here. So you can see that we're dealing with something that is often common in biological data where you have a lot of values that are quite rare. So in this way, we can plot out the frequencies of each of the 2000 odd names together in one single plot for more easy visualization. And we can toggle the names that we include or exclude using the subset criteria that we mentioned before, but you can see that they're all listed here. So that concludes this video on B08 data visualization.